Now that we can visualize that two amino acids can bind with one another via a peptide or amide bond to form dipeptide, tripeptide, oligopeptides, and polypeptides, that is long chains of amino acids, that can allow us to understand that proteins have levels of structures that can form once we have a long chain of amino acids. Now, the first level of structure is the primary structure. That is the linear sequence of amino acids. I've used pipe cleaners and styrofoam toys, cheesy model, to show that we can have, say, a linear sequence of amino acids. We always start reading at the amino terminus. Maybe we have something like proline, threonine, isoleucine, valine, phenylalanine, cysteine, methionine, and this is the linear sequence of amino acids in the polypeptide chain. Red amino 2-carboxyl, this is the primary structure. Now, the secondary structure occurs when local neighborhoods within this polypeptide chain undergo these formation of these structural regularities. For example, one such structural regularity is a helix. We call it an alpha helix, and later we will look at the details of the exact structure of an alpha helix. For now, warrant me this cheesy demonstration that shows that we can see local regularity in structure that is the formation of a helical structure. We term this an alpha helix. This occurs when the carbonyl oxygen of the peptide group, the carbonyl oxygen hydrogen bonds with the amide hydrogen. So if we point that out here, this oxygen will hydrogen bond with a hydrogen on a nearby neighboring amino acid, and it's these local neighborhood interactions with one another that lead to the formation of what we term secondary structure elements. Now, I've shown you the formation of an alpha helix, which we can also draw. You've seen this when you visited the protein data bank, where you've seen the ribbon diagram that depicts an alpha helix looking like this. Another secondary structural element is a beta sheet, much more elongated and linked by what we term beta turns, and forms something that looks a lot more like this. So now when we saw that on the protein data bank and the ribbon diagram, we saw that looking something like this, where we use arrows to kind of help us depict the directionality within a beta sheet and then a beta turn. And again, we'll look more at the details of the structural elements of these. This is a depiction of a beta turn, or a beta sheet, like that. So these are secondary structure elements. Now, of course, in three-dimensional space, these secondary structural elements will interact. So if secondary structure is local neighborhoods of structure, tertiary structure is when non-neighboring amino acids come together to interact with one another. So if this alpha helix over here perhaps interacts with a region of this beta sheet here, and it creates this tertiary or three-dimensional structure to the protein. These non-neighboring three-dimensional structural interactions can lead to the formation of something that we term domains. That is, you'll get sort of this region that groups together and another region perhaps that is distanced from that. So say if, for example, we get an interaction in 3D space like this, where we get this neighborhood up here and then we get another region over here, we term these domains. So we would have one domain up here, and then you've got kind of this extended region here, and then you've got another domain down here. And I can draw this as well. So we would show that perhaps we have this region of alpha helical structure here. Maybe it interacts with some, in 3D space, hard to draw on a two-dimensional page, interacts with some beta sheet. But then there's this sort of long extended region here that links together another whole area I kind of think of this as being like East and West Laramie, where they're connected with one another, but only, in very limited, only through one limited route. So we would get then the formation of these domains. And I'll just go ahead and circle here the domain so you can recognize that. One domain here, and then a second domain there. Now, some proteins are only functional when they are created out of not only one polypeptide chain, but a second complete polypeptide chain. So if we have an interaction between two separate polypeptide chains to form a functional protein, this is termed quaternary structure. So a protein that has separate subunits. So here's a different terminology. This is one subunit, this is another subunit. They interact together to form quaternary structure and are only functional when both polypeptide chains are present. So this would be a dimer of two subunits. So note the difference between domains and subunits. We could have a situation where like this protein has two domains. It has a domain here and a domain here, but then it interacts with a separate polypeptide chain. And maybe this one has two domains. Maybe it has a domain here and a domain here. So we have, in this fully functional protein, we have two subunits, and each subunit has two domains. So our levels of protein structure get to be pretty complex. Primary, secondary, tertiary, quaternary.